In this video we're doing M1 from 2017. First question is pretty straightforward. We've got three forces expressed in terms of I and J. If it's in equilibrium, we can say that the sum of the forces equals 0. So we can just add these three together and use the fact that they're equal and get a simultaneous equation. So we have 15I plus J plus 5QI minus PJ plus minus 3P minus I, again, minus 3PI minus QJ equals 0 because it's in equilibrium. So we can say that we can collect the i's together. We get 15 plus 5q minus 3p I. And collecting the j bits together, we get 1 from this one here minus p minus q. Now, of course, if they're equal to 0, then the I and j both have to be equal to 0. So this bit is equal to 0 here. So we have 15 plus 5q minus 3p equals 0. Let's rewrite that as 3p minus 5q equals to 15. And this one, 1 minus p minus q equals 0, so p plus q equals 1. So we can times that by 3, getting 3p plus 3q equals to 3. So if we subtract these two, we get minus 8q is equal to 12, so q is equal to minus 1.5. Okay, and then if q is minus 1.5, then p must be equal to 2.5. So that's the first question done. So question 2 is a pretty standard momentum and impulse question. We've got two particles, mass 2m, 3m, and they're moving towards each other. So we've got P, which is a mass 2m, going in this direction, and Q coming towards it. Q has got mass 3m, and we're given the the velocities or speeds. 4u is P and 3u is Q. Now, we're told that as a result of the collision that Q is reversed, as its direction reversed. So we know that Q is reversed and it's got speed 3u, or speed u, so that's u there. And it's got mass 3m. This is our before and this is after. Now, you might be able to work out in your head, and the mark scheme does this as well, the velocity of this one's also reversed and marked that on the diagram, but let's suppose we don't know that. And we're just going to assume that P carries on in the same direction. We're going to find out it doesn't, but it doesn't matter, it'll come out in the equations anyway. So that's V, and that's going in the positive direction there, but we'll find that it comes out negative the way we're setting this up. And we'll take this way here as positive. So our momentum equation, conservation of linear momentum, taking forwards positive, we have 2m times 4u, that's that. Take away 3m times 3u, 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 3m times 3 is equal to, now this has come out, this is positive as it is set up at the moment, so it's 2mv plus 3mu. Obviously u cancels, so we get 8u minus 9u is equal to 2v plus 3u. So that gives us 2v is equal to minus 4u. So v is equal to minus 2u. So the way we set this up, we can see that the direction is reversed because we've set it up and it's going that way. But be careful if you do like this, because we're asked for the speed. So we need to say the speed is 2u, speed of p after collision is 2u. And obviously we can see the answer to B, because it's come out negative, the direction is reversed. Okay, so then if we're going to use the, we need to find the magnitude of the impulse. So that will involve using the impulse equation, mv minus u. Okay, so we now know that it's going, if we do it on P or Q, well the impulse on Q is positive, so let's do it on Q. And the impulse on Q will be positive if we take that as positive. So let's do it on Q. So we have the impulse, and the mass of Q is equal to 3m. The final velocity is equal to u. The initial velocity, because we're taking this as positive, is negative 3u. So the impulse is equal to, that's 4u, so that's equal to 12mu. Okay, so now let's look at question 3. We've got a uniform rod, and it's of length 6 meters. And we're told of some supports at 2 meters away from one end, and the support, there's another support somewhere. One person stands. Oh, it's supported at A and C. So here we go. We've got a support A there and support C here. We know it's 6 meters long, so that's, this length here is 2 here, and the other length is 4. We're told something about the reactions. So this is A, this is C, this is B at the end. We're told something about the reactions, where it says something about the reaction at C is 5 times the magnitude of the reaction at A. So if I call this R and call this 5R, and then we've got it all correct. Now it's a uniform rod, so let's put the centre of mass, and the mass of the thing is 30 kilograms, so the weight is 30 times G. And we've got 2 people of mass 75 kilograms at X and 2X away. Let's say 75G and 75G. So let's mark on some distances. Might make sense to go about A. So this distance here is X. This distance here, because it's half of the way along the rod, is 3. This distance here, from here to here, is 2x, because that's given. And then, of course, the distance to the end is 4, because this distance, that length there, is 2. Now, a nice, easy first step here, it's often an easy equation to get, is just to resolve vertically. So we get R plus 5R, forces up, equal to the forces down, 75G plus 30G plus 75G. That gives me 6R equals to 180G. So R equals to 30G. Okay. Right, so the reaction here is 150G and the reaction here is 30G. So then we can take moments about A, as I said, because we've set it, it makes sense because we're given this distances of x here and 2x. So moments are force times distance. Let's look at the ones that are about here which are going clockwise. That's that one, that's the free weights basically, and we've got the reaction force going against it. So this one here, the 75G, times by the distance, not free, it's x, sorry. And then 30G times free. So this the weight of the rod, plus the moment of the other person on the rod, which is 75G times 2x, is equal to 5R, well that's 150G times 4. 15G, 150G times 4. So that gives me, let's work all this out, that's 75G, that's 250G times, that's 150G x there, that's 75G x there, so that's 225G x, and then taking this here is 600, take away 90, so that's 510G. So dividing those, G cancels and we get x is equal to 34 over 15. Now that was accepted in this paper, but I think it's always safe to give two significant figures or three significant figures, 2 if G is used. So 2.7 meters is the answer to two significant figures because of the use of G. Right, okay, and then part B is just a standard modelling thing. If it's uniform, that means the centre, we use the fact that it's a uniform with centre of mass at centre of rod. So that's the fact that it's uniform. Centre of mass at centre of rod. And then the fact that it's a rod does not bend, something like that, does not bend, bend, forces lie on a straight line, or does not bend was enough here, or act on a straight line. Okay, so that's that question done. Let's have a look now at question 4. Okay, question 4 is something we see quite a lot of. We've got something in equilibrium, it's in limiting equilibrium, and it's on the point of sliding down the plane, which means that friction is up the plane. And we have a reaction force perpendicular to the plane, and we've got a weight acting down like that, and we've got the angle alpha that can be put onto our diagram like that. And of course the way we go about this is we're going to resolve parallel and perpendicular to the plane. Okay, so if we look at and then we're going to do it then combine the two. We know also that because it's in limiting equilibrium that the friction is equal to mu r, because it's in limited equilibrium, so we can put that on our diagram if we want. So resolve them perpendicularly, we need to look at forces that are going basically into the plane in that direction. So let's split the 10 Newton force into the component in that direction. We're marking this angle alpha on here, that component there, because it's not adjacent, it's not this component here, it's not this component here we're looking at, it's kind of opposite that, it's not next to the angle mark. That will be 10 sine alpha. And for the weight, which is 5g, this component here is 5g because the angle is marked next to it here, 5g cos alpha. Whilst I'm at it, we can manipulate these angles. We've got tan alpha is equal to 3 over 4. You can use a calculator for this if you want, but I'm not going to here because it's so straightforward anyway. You don't need to write a triangle if you get used to see this a lot in mechanics or elsewhere. If tan alpha is 3 over 4, then sine alpha is 3 over 5, because it's opposite over adjacent. Cos alpha equals 4 over 5. But it's prudent to put sines and coses in our original equation, not 3 over 5 and 4 over 5, so that we get the working. So let's just do our resolving equation. Now what we see is going outwards here in this direction is the r, and then the 10 sine alpha is going into the plane, plus 5g cos alpha. I suppose I could sub in the values of those now. I say it's prudent to not do too much with your first equation, just simply resolve. Don't work too much out, just show what the resolving equation is without simplification. So that's 10 times 3 over 5 plus 5g times by 4 over 5. So that gives me r equals to 6 plus 4g. Okay, now let's do the resolving parallel to the plane. Here we're looking at resolving the 10 Newton force, and this is next to the angle that we've marked, so it's 10 cos alpha. And then this one here, or sometimes people mark it down here, it's up to you, the force down there is 5g sine alpha. So now resolving parallel, we've got the going up the plane, we've got 10 cos alpha. We've also got the mu r, and that's equal to the component of the weight down the plane, that's the 5g sine alpha. Okay, so we can hopefully manipulate all this and get quickly a value for mu here. So let's just do that. Let's put in the 4 and 5 in first of all. So cos alpha is 4 over 5 plus mu r. Let's not do the substitution yet. And 5g is equal to 5g sine alpha. So that's equal to 5g times by 3 over 5. So that gets me 4/5 times that is 8 plus mu r is equal to 3g. Now we can do our substitution. So substitute for r. So we have 8 plus mu times 6 plus 4g equals to 3g. That's substituting for r into there. So just doing a quick manipulation of that, you get the exact value of mu is equal to 3g minus 8 over 6 plus 4g. Now they should accept exact answers, but they don't always, so we better work this out, and that equals to two significant figures I'm going to give. You can give 2 or 3, 2 0.47. I'm giving 2 because of the use of g, although 0.473 is also fine. Okay, so that's question 4 done. Let's now look at question 5. Okay, so this is a dynamics question. It's about a thrust in a rod. So thrust must mean kind of pushing these two apart like that. It's saying it's vertically accelerating vertically upwards, so that's an A, and it's saying that there is a force acting on Q of 15 newtons. But don't forget there's weights on each of these as well. There's a weight of 0.75 G on that one, and there's a weight of 0.5 G on this force as well. So because it's all going in a straight line, it's often a good idea to apply F equals ma to the whole system. Yeah, you can only do that if it's all, you can't do that with pulleys and things, but because it's all going in one direction, it's all fine. Do that, and I tend to apply F equals ma in the direction of the acceleration, so upwards is positive. And the thing is here that the thrust will be will cancel out, but I know we've been asked for the thrust, but we probably need to work out the acceleration in order to work out the thrust. So let's just do that. So F equals ma on the whole system, we've got 15 going up, because we don't have an upwards, take away 0.75 G, take away 0.5 G, is equal to the mass. Now the mass is obviously the combination of the two, so that's 1.25 kilograms times by A. Working that out, 15 minus 1.25 G times 9.8, it's 11 over 4, is equal to 1.5 over 4 A, so it gives me A equals 11 over 5, or 2.2. Now I can apply F equals ma to either of the particles. I'm going to do it to P, because there's fewer forces on P. P has only got the thrust going upwards, and the weight going downwards. Now, people sometimes ask, oh, isn't this force acting like weight? That all gets incorporated in the equations, and this 15 newtons force acting affects the thrust, but it's not actually acting on P. So directly on P there's only 2 T in the 0.5 G equals to the mass of it. Now this is 0.5 times 2.2, so that gives me T is equal to 0.5 times 2.2 plus 0.5 times 9.8, which is equal to 0.5 times these two added together is equal to 12. So that's equal to 6 newtons. Okay, not too bad. The question is a little bit unusual because of the thrust and something moving vertically, but pretty easy once you get the head around it. Okay, let's have a look at the next question. So here we have equations of uniform acceleration, or SUVAT equations question. We've got a cyclist moving along a straight road, passes through point A. 5 seconds later, at the instant is moving with speed 10 meters per second, it passes at point B. She moves with constant acceleration from A to B. And 5 seconds later, at an instant that says 10 meters per second, let's call that 10 meters per second at point B. And what else are we told? 5 seconds, we know that T equals to 5 there. And we know that the distance from here to here is 40. So we know S is 40, so we're looking for the appropriate SUVAT equation. There's 5 of them, which we probably should use. This one, probably the least used one, is the one that involves the 3 variables that we've got, that we're dealing with here. V, T and S which we're given, and A which we're trying to find out. So put that into here. 40 is equal to 10T minus a half times A times T squared, which is 5 squared. And I knew 5, I had 5 there of course as well. So 40 is equal to 50 minus 12.5a. So 12.5a equals 10, so a equals 0.8 meters per second squared. So that's the first part done, just choosing the appropriate solver. The second part is talking about the midpoint, and it wants the time it takes to get from A to C, the time it takes to get from there. Now, we don't know the speed at C or the speed at A, or the velocity, whatever, A or C, which we're going to need to find out, because otherwise we've only got 2, we really don't know enough. We know that the length is 20 here, because it's the midpoint, and we know that the acceleration is 0.8, but we need to find out one of the other things so we can work out what the velocity at A is. Let's call that u. Okay, so if we apply v is equal to u plus at for the motion A to B, because we're splitting this into different bits. To make it clear, it's from A to B we're applying that for. Now the velocity at B is 10, and u is what we're trying to find out. A we now know is 0.8, and we know the time taken for that time is 5 as well. So that just gives us u equals to 6. Okay, so we've got u equals 6. Once we've got that, it should fall out quite nicely, because we now know that u equals 6. We also know that s is 20, because we're now going from A to C, because we want the time it takes. We want the time it takes to go from A to C. We know the acceleration is 0.8. And we also know now that u equals 6 from that. So we can use s is equal to ut plus half at squared. So s is 20 is equal to ut, so that's 6 times t plus half times 0.8 t squared. So that gives me 0.4 t squared plus 6t minus 20 equals 0. Well, you can put that straight into form if you want. Just have an overwhelming temptation to make it positive coefficients, so I'm going to times by 2.5, because timesing that by 2.5 will make that t squared. Just make it 1, times that by 2.5, we get 15t, times that by 2.5, and we get 50. So we can then say t is equal to minus 15 plus, we don't need to consider the negative one here because that will give us a negative time, 15 squared minus 4 times by 1 times minus 50 all over 2 gives us minus 15 plus 225 plus 200 over 2, and when we work that out, that gives us 2.81. Two pretty significant figures, 2.81 seconds. So that's that question done. Okay, so we've got a couple more questions to do. Question 7. So question 7 is vectors, motion question, the constant velocity, and i's and j's, fairly standard stuff really. See a fair few of these over the years. We've got something p that's going in the direction 9i minus 2j, going with velocity minus 9i plus 9i minus 2j, like this. 9 across and 2 down. And we want the direction of motion given it as a bearing to to the nearest degree. Now the bearing is measured from the north clockwise. So this angle here is alpha here. And once we've worked that angle alpha out, we want this angle, we want the bearing north, which is slightly more than 90 if you look at it. So we can work out tan alpha, which is opposite of adjacent, which is 2/9. So if we work out the inverse tan of that, (2/9) that's 12.5 degrees. Okay, so the bearing, what we've been asked for, is 90 plus that. It's 52 degrees, and it wants to go to the nearest degree, so that's 103 degrees. Right, for part B, there's just finding the general expressions for the position vectors, and we can use this formula. Final position vector after time t is equal to the initial position vector when t equals 0 plus the velocity times time. So they've said that the position vector p, we're calling it p at time t, so p is calling p the position vector after time t, is equal to the initial position vector, which is this one here, 9i plus 10j, plus the velocity, and the velocity of p is this here, 9i minus 2j times t. So that's enough for the mark, but we're going to need to tidy it up in the next bit anyway. So it's 9 plus 9t I plus 10 minus 2t j for that one. And then we can do the same for q. Q is initially at I plus 4j, and it's going at this velocity, so that's plus velocity times time, 4i plus 8j times t, and organising that accordingly, we get q is equal to I, put the I afterwards, we get 2 is equal to 1 plus 4t I plus 4 plus 8t j. Okay, so 3 marks for that. Now for the next part, C, it wants the position of P relative to Q, the relative position vector of Q. What I like to do here is basically do a diagram, put Q here, say, P here, doesn't need to be accurate. This is the position vector of Q. This is the position vector of P as it's been set up. We want QP. So QP, so that we've got the right way round, is equal to minus Q plus P. So that equals to minus 1 plus 4t I minus 4 plus 8t j plus p, that's 9 plus 9t I plus 10 minus 2t j. And that's going to give us what we need, I think, QP. I think that's enough, really. Minus 1 plus 9, that's 8. And minus 4t plus 9t, so that's plus 5t I. And then for this one, we've got minus 4 plus 10, that's 6. That's minus, and then minus 8t minus 2t, that's minus 10t j. Okay, so then it asks for the two times when they are 10 kilometers apart. So we basically want to find out the two times when this is true. Okay, when the distance is, because distance is magnitude of, this is the displacement really, the relative position vector of 1, or the displacement from Q to P. So we want the distance at the times when the distance is 10. So that basically can be summarized, and this is the magnitude of this vector, and we know the magnitude of a vector A plus BI AI plus BJ is equal to, using Pythagoras, A squared plus B squared. So we have 8 plus 5t squared plus 6 minus 10t squared is equal to 10. So squaring that out, we're going to get equals to 100, and squaring each individual bits out here. 8 squared is 64. 5 times 8 is 40, but we're doubling that, so it's 80t plus 25t squared. 6 squared is 36, and then we have minus 10t here, that's minus 60 minus 122. Okay, so it's 60 times 2 plus 100t squared is equal to 100. So tidying this up, we've actually got 64 plus 36 equals 100, which cancels with the 100 here. So we have 125t squared, and then we have the 125t squared, and then we also have the minus 120t plus 80t, so it's minus 40t equals 0. So take it, we can divide that all by 5. So that gives us, dividing that 25t squared minus 8t equals 0. T times 25t minus 8 equals 0. So we have t equals 0, or t is equal to 8 over 25, which is 8 divided by 25 equals to 0.32. Let's check the actual context of the question. If there's any hours, it's all in hours, 0.32 hours. Doesn't really talk about times of day, so I think we're okay here. So that's t equals 0 and t equals to 0.32, which is the final. Okay, final question. Quite a long one. See this type of thing quite a lot though. Dynamics, connected particles, that kind of thing. We've got two particles connected over a rough table, your unknown coefficient of friction, lots of kind of algebra in this, fewer numbers until the end. Right, so let's just do our diagram. We've got a weight 2 mg there, got a reaction force here, we've got friction acting back on that, which is mu r, because we know it's going to be moving. The tension there, obviously it's tensions around P, but the force doesn't ask, the question doesn't ask about forces on the pulley or anything like that. Got T there, we've got mg here, and we know that it's accelerating downwards. It couldn't do anything else. It was either going to stay stationary or going to accelerate downwards like that. We're told that it moves one way or another in that direction. So we're just going to apply F equals ma to find these two equations for the motion of A and B. F equals ma to A, well, we can just say that it's accelerated in this direction. I've got T minus friction, which I'm just going to write as mu r at this stage. Well, for the marking, just put F, it doesn't really matter, is equal to mass, which is 2m times acceleration. And then for B, for this particle here, we've got going downwards mg, T going upwards is equal, and the mass of this one is m, and that's A. So that's our part A done. Part B, just to combine those two really, we've got R equals to 2mg anyway, because it's resolving vertically, which tells us that T minus mu to 2 mu mg equals to 2ma from this equation there. Equivalent thing. And we've got mg minus T is equal to ma. So if we add those two, we get mg minus 2 mu mg is equal to 3ma. Obviously the a cancels, so we have 3a is equal to, taking g out as a factor there, g times 1 minus 2 mu. So a is equal to g over 3, 1 minus 2 mu. Okay, so that's pretty okay, setting, all working out fine so far. Part C is to work out, in terms of g, h and mu, the speed when B hits the floor here. Well, we're given h as the distance it actually takes, it moves till it hits the floor. So we know that u is 0. We know the acceleration is this thing here. And we also know that S is equal to H, and we're being asked for V. So we're going to apply V squared is equal to U squared plus 2AS. So V squared is equal to U squared, which is 0, plus 2 times the acceleration, which is g over 3 times 1 minus 2 mu, times h. So that gives us, this is just 0, 2g h over 3 times 1 minus 2 mu, that's mu v squared, so v is equal to the square root of that. So now we need to look at the, we go into some slightly longer parts. We're now given that mu equals to 1/3 and find d in terms of h, and we're basically told a few things here. Let's draw that diagram again down here. We've got we're basically told that the distance from here to here is d, but it will have originally moved h from there to there before this hits the ground. Here. Now after this particle hits the ground here, the string will become loose. And at that point there's friction, but there's no tension, so the string becomes loose, and we just have friction going in this direction. And the friction is equal to 2 mu mg, because r is equal to 2 mg. And it's just going to decelerate, so we want to find this extra distance here in terms of h. So, because we're told that it stops exactly on the pulley, where that is. So the screw is now loose, but what we need to do is work out the speed of this thing when it becomes loose. When string becomes loose. Well, that's going to be equal to whatever this is, due, because basically whilst it's moving from here to here, it's accelerating with this velocity, and it's ended up with this acceleration, it's ended up with this velocity, and that will be the velocity it will have gained when it's got to this point when the string becomes loose, because this bit's hit the ground. So we can say that u is equal to the square root of, but we know that mu is equal to a third, so that's 2gh over 3, 1 minus 2 times a third. So that equals to square root of 2gh over 3 times by 1/3, or the square root of 2gh over 9. So that's that velocity there. Now we need to work out the deceleration. Because the only thing that's slowing it down, the only force on it now is friction. So we can say that minus deceleration 2 times by a third mg, because mu is a third, we're told it's a third now, is equal to the mass times acceleration, which is equal to 2ma. Obviously m cancels. So we can say that a is equal to minus a third g. So we've got the velocity when it started to decelerate here, the strings become loose, which is this, and we've got the acceleration. Let's call this extra distance here x, that it moves between the pulley. So then we know that the final velocity there is 0 because it comes to rest at the pulley. So we've got v is 0, we've got a is equal to minus a third g, we've got u is equal to the square root of 2gh over 9, and we want to find s, which is equal to x. So we're going to use v squared equals to u squared plus 2as. So we can say 0 squared is equal to u squared, which is 2gh over 9, plus 2 times minus a third g times by s, which we're calling x. So cancelling out g, we're going to get that's 0 2h over 9 minus 2/3 of x. So timesing that through by 9 and cancelling out the 2 as well, you'll get that x is equal to 1/3 of h. So we can now write d in terms of x, because d is equal to the h it's travelled whilst it's loose, whilst it's taut, whilst in that accelerating phase going all the way back here, plus the bit whilst it's slowing down where the string has become loose, that's plus x. So d is equal to h plus a third h, so that's 4 over 3h. Okay, so that's nearly done, the whole paper. There is one mark at the end. Describe what happens when mu equals half. You may have noticed this thing written in the question here, if mu is less than half. It's not defining the question carefully, because if u were equal to half, or indeed if u were more than half, it wouldn't move. If you look at the acceleration here, this here would be, if you put mu equals to half in there, you get 0, a is 0. And of course half is the smallest value where there is no acceleration. So we can just say that it's in limiting equilibrium. We don't have to say it's in limiting equilibrium. We can just say it doesn't move. The mark scheme gave it, that's probably the more precise answer, but the mark scheme does not move. In fact, it won't move if mu is any greater than half. But if it's actually equal to half, it's just on that point where it would be on the point of moving. So mu greater than half would be doesn't move, non-limiting equilibrium if you like. Whereas if mu equals to half, limiting, so non-limiting, but either way it doesn't move. And of course if mu is less than half, we've got the situation we've just been working on with it being accelerating. Okay, so that's it. June 2017 done. I hope you found the video useful. Thanks, bye.